All right, so we're going to walk you through this typical problem of a modern physics problem from an AP exam. In this problem, a photon collides with an electron. This is called the Compton effect. All right, photon-electron collisions. In this problem, a photon with a wavelength of 2 times 10 to the minus 11th meters strikes a free electron of the massive electron. On the front page of your equation sheet, you'll see the mass of the electron is 9.11 times 10 to the minus 31 kilograms, which is initially at rest, as shown above. After the collision, the photon is shifted by a wavelength of this much and reverses direction. Determine the energy in joules of the incident photon. Okay, energy equals HF. We're not given F. Instead, we're given the wavelength, but that's okay because this works out. Energy equals H. Frequency is the speed of light divided by the wavelength. So now energy equals Planck's constant, 6.626 times 10 to the minus 34th joule seconds, multiplied by the speed of light, 3 times 10 to the 8th meters per second, divided by lambda, which was 2 times 10 to the minus 11 meters. You do all this math, energy equals, you should be coming up with 9.939 times 10 to the minus 15th joules. That's the energy of the incident photon. Determine the magnitude of the momentum of that thing. It has energy, but what's the momentum of it? I don't know. What do we know? There's this equation in reference tables. H over momentum. We want to know the momentum. Momentum is equal to H over lambda. H, 6.626 times 10 to the minus 34th joule seconds divided by the wavelength of 2 times 10 to the minus 11 meters. So the momentum of the incident photon equals, grab the calculator for a moment, 6.626 second E negative 34 divided by 2 to the negative 11th. And you get 3.313. 3.3, darn it. Clean that up. 3.313 times 10 to the minus 23rd kilogram meters per second. That's momentum. So there's the first two parts. 9.939 times 10 to the minus 15th joules and 3.313 times 10 to the minus 23rd kilogram meters per second. Now in this collision, what's going to end up happening? Indicate whether the photon wavelength is increased or decreased by this interaction. Okay, momentum has to be conserved. Momentum will be conserved, always in collisions. Big collisions, small collisions, it really doesn't matter. Momentum is going to be conserved. So if you think about this, the answer is going to be increased, but let's think about it. Wavelength coming in of light, so some kind of a gamma particle, some photon there, gamma would be the symbol for that, interacts with an electron. So you got some MV of this thing. This thing is at rest, so it has zero momentum. Afterwards, you get some photon, some gamma particle going the other direction, and the electron is going this way. So the initial momentum is coming all from this thing. initial momentum, because this thing has zero momentum. This thing goes off with some mv. If this thing takes some momentum or gets some momentum, which it originally had none, it's got to get from here. So what's going to happen? And this is how I'm explaining the reasoning here. Oops, that's a terrible box. Explaining the reasoning here. Since momentum is conserved, if the electron, which had zero momentum to start, gets some momentum, it's going to take momentum away from that initial photon. And according to this relationship, wavelength equals h over momentum, or we could flip it around and say momentum equals h over wavelength. If the momentum of a thing increases, its wavelength decreases, or vice versa. If the momentum of a thing decreases, if the momentum drops, that means the wavelength must increase, which is what's happening here. The momentum of the gamma particle has got to decrease. The momentum of the photon's got to decrease. It's going to impart some momentum to the electron. So as the momentum of this thing drops, the wavelength is going to increase. Now, the last part of this problem, a little tricky math. Determine the magnitude of the momentum acquired by the electron. Well, you're told the change in the wavelength is 2h over the mass of the electron times A. That you're given that. Okay. Here's a very, very important concept that we've talked about a lot. But anytime you have a change in anything, a change in x or a change in y or a change in momentum is always x final minus x initial. It's always the final minus the initial. So here you're given the delta, and they want to know the final. So we can talk about it as wavelength, delta wavelength equals the wavelength final minus the wavelength initial. We were given the initial wavelength. We have the delta. We need to find this. The initial wavelength, let's actually do some algebra first. We want to find the final wavelength. So lambda final will be equal to, we'll bring this over there, will be the change in wavelength plus the initial wavelength. Right, I can change colors for a moment. I can bring this over to that side of the equation and go from there to get the final. So, the final equals 2h over MEC plus initial 2 times 10 to the minus 11th meters. Do all this math. 2 times the Planck's constant squared, Planck's constant, 2 times 6.626 times 10 to the negative 34th gives you some number. Divide that by the mass of electron, 9.11 times 10 to the minus 31st, and also C, 3 times 10 to the 8th meters per second. That's not right. Should be 2.5. 2 times 6.626 second E, negative 34 gives you that number. Take that number and divide it by the mass of the electron, 9.11, second E, 31, and also 3 times 10 to the 8th gives you that. Add that to, whoa, I hit the wrong button again. Darn it. I got a number to the negative 74th. That can't be right. That's wrong. But I see where I messed up. I didn't hit negative 31. I hit positive 31. Try this for a third time. See if I can hit the right buttons. 2 times 6.626 negative 34 gives you that. Divided by 9.11 second E negative 31. There we go. And then I'll divide that by 3 second E 8 gives you that. So basically we're getting this. And the final equals 4.8488, a bunch of other numbers, times 10 to the negative 12 meters, plus 2 times 10 to the minus 11 meters. Lambda final will be equal to, should be just around, there we go. That's the right number. 2.48, 2.485 times 10 to the minus 11th meters. That is the final wavelength. Determine them, but that's not what they wanted to know. Darn it, they want to know the momentum acquired by the electron. Oh, so this is the new wavelength of the photon. We know the momentum at the beginning of this thing, so let's find the momentum of this. The momentum equals h over lambda. So let's divide this by h. So we're going to get, this would be of the final wavelength, the final bit of light here. So 6.626 times 10 to the minus 34 joule seconds over this wavelength, 2.485 times 10 to the minus 11 meters. So the momentum of the bit of light is now, let's go 6.626 second negative 34th divided by our last answer, and we get 2.667, right? Yeah, 2.667 times 10 to the minus 23rd kilogram meters per second. Now, the momentum was this, right? The momentum of the initial thing plus the momentum of the electron, which is 0, will be equal to the momentum of the final photon plus momentum of the electron. Guys, I'm recording a video, just to let you know. So let's see, what do we got going on here? This thing was 3.313 times 10 to the minus 23rd. This thing was 0 equals this thing, 2.667 times 10 to the 23rd. And now we need to find the momentum of this electron. So it's going to be 3.313 times 10 to the minus 23rd, the difference of 2.667 times 10 to the minus 23rd. Let's see what we come up with. 3.313 times 10 to the minus 23rd, subtract 2.667 times 10 to the minus 23rd, and we come up with the momentum of the electron after the collision equals 6.46 times 10 to the negative 24th kilogram meters per second. There's your answer.